the sine of A over little a. You could have used sine of big B over little b, or sine of C over little c, but since it was found, I like to use the A if possible. Most teachers will recommend it to as well. Sine of B over angle B, which is 34 degrees over little b. That's what we're trying to find. Is equal to the sine of 64 degrees divided by 5.6. We cross multiply. Let's see if we got that right so far. Yes. 5.6 times the sine of 34 is equal to b times the sine of 64. And so for b, it's 5.6 times the sine of 34 divided by sine of 64. To solve for b, we divide it by the sine of 64 to the side. And using my calculator, I'm going to just say it as I go. 5.6 sine of 34 and 10 divided by the sine of 64. 3.5. And so little b should be 3.5. Let's see if you got that right. From the book, yes it is. Little b is 3.5 and little c is equal to 6.2. 6.2. Perfect. I'm gonna give you a little bit of a note on this one right over here. And if it quacks like a duck, it flies like a duck, it tastes like a duck, it walks like a duck, it's probably a duck. And so I'm going to show you a little bit of a real quick, not quack, quick check. Some teachers, some of the good teachers know what the quick check is. It takes about 5 seconds, literally 5 seconds to do. If you know how to do this quick check, you'll be fine. I'm just going to exaggerate a triangle out this way, like this. And I'm going to figure out what the biggest angle is. Out of this one, the top one, the left one, or the right one, the biggest angle seems to be this one. And the smallest angle seems to be this one right here. And obviously this is the middle angle. Capitals. Notice that all capitals. Notice that in this triangle right here, the biggest side seems to be opposite the biggest angle. So I'm going to put little b right there for the biggest. The small side is right here. And the middle angle is right here. You should know that makes kind of sense. It's like a quick check. So let's go back in here and let's put in the number 6.2 and little b is 3.5. Let's use this armed with this information, the quick check. Biggest angle, biggest side. Smallest angle, small side, and that's all we need to check. Biggest angle, biggest side, smallest angle, small side. Obviously, the middle ones will be right in between, just right. Okay, so let's do this one right here. Biggest angle is this. Is it the opposite the biggest side? Yes. The smallest angle is here, opposite the small side? Yes. Out of these three sides, this is small side, smallest angle. Biggest angle, out of these three, biggest side. Oh, literally took 5 seconds, guys. Make sure you understand how to do the quick check, not the quack check. If it seems to fly like a duck, it's probably a duck. Or walk like a duck, or quack like a duck. Okay. Example 3. I'm going to do 4 examples. I'm going to draw it out for you because it's kind of like this is example 4 from the book. Okay, and here's the Earth. Let's something like this, and then from the center, here's point C right there, and this is point A right there, and this is point B right here. You're on the Earth. That's a satellite, and this is point D. Should have made this a little bit bigger. So C is the center, B is at the edge of the Earth, A is where the satellite is. and D is at a different point. It says right here, the satellite is circling above the Earth in this figure. As a site directly above B has an angle A of 74.5 degrees. So that's so we're going to redraw the triangle out. 74. That right there is 74.5 degrees. If the distance between B and D on the circumference of the Earth is 910 miles. So I'm going to redraw it out like this. 910 miles. And the radius of the Earth is 3,960 miles. Approximately. This from the center of the Earth to the edge is about 4,000 miles. So they're pretty accurate with their numbers. 3,960. You can Google that if you want. It's probably 3,960 is a little bit closer than mine, but I approximate it at about 4,000. That's a pretty good number to deal with. How far above the Earth is the satellite? So this is what we're looking for. Okay? So how far above the Earth is the satellite? Okay. This 910 miles is going to be pretty important stuff. So first let's do this. How did they do it? I don't know if I want to do it the way they did it or not. Okay. Alright. Well, let's see what they did. We're trying to find this angle first. This angle C from the center. This is going to be 910 miles. Since we're looking for the arc length, does anybody remember the arc length formula? Oh, I do. No, actually, not many people do remember the arc length formula. S is equal to r theta. And don't forget, this is going to be in radians, and S is going to be in the arc length. So arc length is equal to the radius times theta. I believe it's in chapter 3 of this book. Don't quite remember. This is the trigonometric way. So the arc length, 910, is equal to the radius, 3,960, times the angle theta. Solving for theta, 910 divided by 363960. See? And we end up with 0.23 theta is approximately 0.230 radians. To convert this to radians to degrees, put the radians here, put the degrees right here. Pi radians is 180 degrees, so we're going to take this number, 0.230, multiply by 180, and then divide it by pi. It's approximately 13.2 degrees. 22 minutes is left. Yeah, we're going to try to finish this up, and maybe one more question. I might do one more extra. I might do example number 5, or actually, I lied. I'm probably going to do just 3 examples. So, let's draw this again. Here's how it goes. This is 3,960. This is what we're looking for. Let's call this x right there. This is going to be 3,960 plus x. We know what this angle is right over here. It's going to be 13.2 degrees. Do we know any other information other than that? Let's see. Look at the book here. Side of the angle. Do we know this distance right here? No, we don't. Oh, they're also given this right here, 74.5 degrees. So we're going to add them all up, subtract it from 180. 180 minus 13.2 minus 74.5. Oh, let's do that again. I made a little bit of a mistake. Here, 74.5. That's going to be 92.3. I'm going to try to draw this nice and big for you, okay? 13.2 degrees, 74.5 degrees. This is going to be 92.3 degrees. So that's 92.3, 74.5. I subtracted from 180 from these two. This is 3960 plus x. Do we know what this length is, CD? Right over here, CD. Oh, that's the radius. So this is 3960. So you could use the SAS situation or the ASA situation. Or, I'm sorry, AAS, or SAS, ASA, excuse me, ASA. So we can use the law of sines. Sine of 92.3 degrees divided by the opposite side, 3960 plus x is equal to sine of 74.5 over the opposite side. Sine of 74.5 degrees over 3960. We cross multiply, you get 3960 times the sine of 92.3 is equal to 3960 plus x times the sine of 74.5. And we can distribute at the stage, or since these are being multiplied, I can divide it by, let me use another pen for this, divide it by the sine of 74.5. I end up with this times this, so I divide it by that, and that's what I end up with. So I end up with 3960, right over here, 3960 plus x is equal to that. How do I solve for x right here? I subtract 3960, and you end up with x. How far away from the satellite, from the Earth? The edge of the Earth to the satellite. That's the distance that we're looking for. So I'm going to do this on my calculator. 3960 times the sine of 92.3, enter, divided by sine of 74.5, and then enter that, and then subtracted 3960. Okay, I end up with approximately 146. So x is approximately 146 miles from the Earth. Let's see if I got that right. Oh, I didn't. It says 131 degrees. Let's see if I did that right. 3960 times the sine of 91.4. How did I get 92.3? 92.3. Let's do this one. Is this 74.5? Oh, 75.4. I miswrote the problem. I put 74.5. We're going to get a different answer, but you should be able to get, because I wrote it as 74.5 instead of, made a mistake right at the beginning. This should have been 75.4 degrees. Miswrote the problem. Miswrote the problem here. You're going to get a different degree here. You can get just a little bit